Hello everyone. I'm Elliott. I work at Epoch AI for now, a nonprofit research organization studying the capabilities and trajectory of AI. And I was brought aboard this organization about a year ago to run this project, FrontierMath, a math benchmarking project. This is Epoch's first in-house benchmark. For the most part, our org is happy to use any resources available to study models, including benchmarks that already exist. But we developed FrontierMath to fill in a niche that we didn't think anyone was filling then or in the near future. The niche being a genuinely hard math benchmark that was not about to be imminently saturated. So this was a necessary development to help us properly analyze how good models are getting in mathematics. So we've talked about this benchmark probably to mostly one-on-one by now, and also, frankly, many times in conversations over the past year. So I figure due to the relatively high concept of this conference, I would approach the talk with a little more high concept way. So I'm gonna start things off with a thought experiment. So there are only finally many computer programs that take up, say, 1 petabyte of storage space, which is way bigger than any currently existing model, and almost certainly well beyond the amount of storage that it would take to formalize whatever mathematical architecture is being used in each of our brains. So of this many possible combinations of bits, which one will produce the best math intelligence? And just to make this question a little bit more concrete, so we have this fixed amount of storage space, and you allotted some amount of time and computational resources to tackle all the most 100 most important math problems as rated by some survey that could be conducted today. And which one would do the best? What would it look like? Would it be some sort of LLM? Would it be a lean autoformalizer? An energy-based model? Would it be closer to humanity, something like several simulated mathematical consciousnesses representing the greatest mathematicians of all time working together over eons to solve the hardest problems? Or maybe I shouldn't be thinking in terms of a few Ubermenschen, but rather just like a large community of simulated mathematical consciousnesses working together, trying as many ideas in parallel the way our community does in the real world. My guess is we have no idea yet what actually takes to build any sort of model like this, or anywhere near mathematical intelligence perfection. So my guess is it's going to be some sort of inscrutable combination of the above, and it's going to involve many breakthroughs that we are nowhere close to. But one guess that I have that has guided me in my work the past year is it is going to get built. That within some epsilon, we will get pretty close to whatever architecture is optimal for reasoning about math. Sure.
Um, I think it's well accepted that intelligence is not really a one-dimensional thing. Maybe mathematical intelligence is also not one-dimensional. Maybe you can be really good at one particular sub-area and really bad at another sub-area. Maybe if you want to go extremely deep in mathematics, you really need that specialization. So maybe your first question of the best possible mathematical intelligence is already like not well defined.
I agree, and this will come up on this very slide.
Okay.
So what have I described right now? So I gave some parameters, the amount of space we have, the set of combinations under consideration, and at the very least, a very crude objective to optimize towards. And what do you know? We have a lot of technology these days for getting models to be optimized on a task that is defined for it. But It's not as easy as that because first we do have to actually come up with some reasonable way to quantize and measure mathematical ability. And how do we do this, especially once we get past the level of math ability that grade school exams get used for? Professional research mathematics doesn't get graded on a scale, and none of us have gotten letter grades in a very long time. So yeah, I gave a crude operationalization for one potential end objective, efficiently solving today's most infamous math problems. But we can't just optimize directly for that in a vacuum. That's about as sensible as, to borrow something that Mike quoted yesterday, the Wright brothers' aviation progress by number of successfully completed flights. Like, it's a metric that would just be 0 for ages, not showing any sign of progress until a problem is solved. So that doesn't help. So we would need a lot more sophisticated metrics than what anyone has currently conceived of to put this thought experiment into practice. But that's sort of my overarching goal when I'm thinking about how to build a benchmark. I'm not thinking about how to challenge particularly today's models. I don't necessarily care when I make a benchmark if it's going to be reasonable for today's models or if it's likely to be saturated within the next year. I want something that when eventually does come to pass that this gets solved, this gets saturated, that would demonstrate substantial progress in the ability for machines to do math. So some vague criteria that I think at least somewhat clarify the goal here. So a good large-scale benchmark should have an extremely high difficulty ceiling. It can't just be a bunch of problems testing standard knowledge. That might be what the general public thinks math is about, but really what we're looking for are entities that are capable of generating vast original discoveries. It should be automatically tested. There should be a way to verify how well a model is doing on math problems without having to have a human preside over grading at every step. This is useful for a lot of purposes. If this metric is being used for a training run, obviously the scale of these is so vastly beyond the point where we could really be having humans judging things line by line. But even if it's just for a publicly analyzed benchmark to document the progress of all the main models out there, it would really be unfeasible if every time a new model comes out, there has to be several humans on staff ready to see what kind of results are coming out. Yes?
Yeah, would you want multiple different benchmarks, say one for going for birds and then one going for the frog types. So then you get someone who's like, then you get a bunch of the agents who are like a Witten type and do like far reaching stuff, and then a bunch of others that are more like the frog type that are ones that are actually making sense of it.
I mean, sure. This is why in my list of hypothetical models for mathematical superintelligence, one was this idea of maybe it doesn't make sense to just say we have a few mathematicians who are the greatest and those should be our model for what math is. It could be, yeah, many different types of analysis working together might be most fruitful in the long run. Combination of problem solvers and theory builders working together to efficiently develop our understanding of structure. That's quite possibly a better model than just focusing on just one specific thing. So we want automatic testing and verification, but at the same time, we don't want a metric that becomes contrived and completely awry from what mathematicians really care about. So if a huge jump occurs on a benchmark score, it's important that when human mathematicians start looking over the results and seeing what the models are up to get this performance, it actually is demonstrating to humans as we understand mathematics to be very good work. You should want a gradual increase in score as capabilities improve. So to avoid, so we don't want a metric like the number of flights that have been occurred or number of millennium problems solved, which again is the kind of metric that just gets stuck at 0 for ages and doesn't provide any signal in the short term. It should be well calibrated in difficulty order. So most benchmarks aren't intending to capture one homogeneous difficulty. Usually there will be a bunch of items ranging from the easy items, things that are seen as only barely out of reach of current technology, up to much further reach problems to see when things are really getting spicy. But if it turns out that the hard problems on a benchmark are getting solved before many of the easy ones, that might be a sign that the way that these problems are being scored is a bit too tailored to human understanding of what difficulty looks like, and maybe not well calibrated to what are the actual skills that are harder for models to acquire. And yeah, bring up the point that was brought up a few minutes ago. We do want a really good math metric is probably not just going to be a score of 0 to 100. How good are you at the math? There are many types of mathematical reasoning. In real life, if you compare humans against one another, we each have excel in different ways. And one example being the mentioned division between theory builders and problem solvers, and also the differences in techniques and skills and approaches used between the many subfields of mathematics. So it may make sense to have many metrics simultaneously being analyzed, but still possibly concatenating them in some way to give at least some rough overall score of how things are coming along. So let's now get back to what was my own first benchmark, which was FrontierMath. FrontierMath is a benchmark of 350 problems which were developed roughly over the past year by my org Epoch AI in collaboration with OpenAI. One funny thing a little about the backstory of this collaboration, which I only have secondhand witness to. I only joined Epoch after this collaboration began and this project was funded. But when my predecessors at my org were first pitching this project and showing them a pilot, it was actually a lot easier than the project ended up being. And the reason for this pivot towards a much harder project was OpenAI's warning my bosses that if you make more problems of this difficulty, it's going to be saturated before you're even done making it. So that warning helped calibrate the team towards a need to actually make things really hard and beyond what we thought were even potentially reasonable for models in the near-term future. So what does an item of this benchmark look like?
It was just a bunch of mathematicians making this benchmark, just math.
Yeah, this is all math. And what the items look like are each one is a math problem. Natural language, original, none of them can be found in textbooks. Each of them asking for some closed form value, usually an integer, sometimes a symbolic real number, sometimes a tuple of them, and occasionally more customized inputs that have some that are designed to add to test some specific combinatorial structure. But the point being that what the models are not being asked to provide is proofs. So since this is a natural language benchmark, it really wasn't on so the combination of natural language and wanting automatic verification means that it was not a non-starter to have proofs involved in it. So instead, the idea is that these are problems that are designed such that they're big, unguessable integers or reals that you really are unlikely to guess them without a model genuinely working through the problem's underlying mathematics.
But are they in NP? And once you have a correct guess, you can verify?
So for the ones that are just integer problems, the check is simply the author gave us the answer. These are not problems, these are not open problems. These are like test items that are designed with a specific answer in mind, designed to test a particular skill or research area.
problems with a more complicated answer that you could still verify, like the answer to the function, put out a program that computes or approximates that function. Did you consider that?
We have considered that. We did want the inputs to be relatively constrained in nature, but there are a few ways in which certain problems do subvert the formula a little bit. Like some of the problems are Diophantine equation problems, where there actually is not a unique solution. The author provides us with their intended solution, but they also acknowledge that there will be other integer solutions. So for those, the verification script is literally put the integers into the polynomial and see if it works out. But for the majority of problems, it is an actual equality check against what we already have. So the writers were about 100 mathematicians, mostly grad students and beyond. And feel free to peruse some of the sample problems while I'm talking and see how the items on the sample webpage compare to what I am saying they're like. If you just typed in this URL or Google FrontierMath benchmark problems, it should be easy enough to find this webpage. And if you are multitasking, a thought to keep in mind throughout the talk is which of the ones that you're looking at seem like they're going to be the ones that are trickiest for AI? Because some have been solved, some have not been solved, and I'll tell you exactly which ones are which near the end.
We're going to talk about the process of soliciting the problem. So,
That's not going to be too much of a focus for this talk. I'm free to talk about that more in questions. But I'll talk right now about the structure of how the final data set is laid out. So the initial data set was 300 problems, which are split into three very rough tiers of difficulty. Tiers 1 through 3 with a 20%, 40%, 40% distribution ratio. The tier 1 problems were the ones intended to be things that seem to be just outside or just within reach of what we expected models would be able to do when we were making this. So that was mostly IMO style problems and advanced undergraduate exercises. Tier 2 is problems where usually qual problems are graduate coursework. So using ideas and knowledge that usually only becomes available to a mathematician very far into their studies. And tier 3 is very roughly defined to be sort of like an exploratory research project. Like a problem an advisor might first give their PhD student, one that they perceive as being completely solvable, probably within a short amount of time, but just getting their feet wet with turning their technology into some sort of original argument. And progress on these first 3 tiers was a lot faster than we expected. The first really big shock came last December when OpenAI announced that they got 25%. Not when we ran this on them, but they did an internally scaffolded run with O3 right before they announced O3. And this got a very high score of 25% that was for some time unreplicable due to them presumably putting a lot of scaffolding and resources into it that we are simply not able to do on our end of the evaluations. So it's not an apples to apples comparison, but I can generally say that even knowing that they had these advantages, I would not have expected 25% for at least another year or two after they announced it. And if there was any doubt, the score is now publicly achieved by GPT-5. So on our evaluations of it, that's the score they get. And over half of the data set are problems which have been solved at least once and at least by one model in some evaluation.
What percentage of the tier 3 problems solved?
Don't have the statistics off the top of my head. It's definitely less than the other categories, but it's not as far off as you might expect. Turns out it's pretty hard for us to guess what actually will stump a model in advance. So I'll say a little more about that when I give a meta evaluation of my evaluation.
So just following, I mean, so it's not like all 20% and all 40% are solved, none of the.
That's right. Yeah, I think it's like 80% of tier 1 have been solved at least once, closer to 30% of tier 2, and I think it was like 20% of tier 3, something like that. I can get you the exact statistic later. So yeah, we realized this point of, yes.
As far as being able to say what, trying to guess what they can do in advance. So as the idea from RASP-L, but that's so I've seen that as far as computer programs that they can do. Any comments on RASP?
RASP?
That's really a different thing. We can
Yeah.
talk about that at the questions.
I'm not sure what that is. But yeah, so this was around the time when we decided that we were no longer confident that the original FrontierMath dataset would survive AI attacks for more than a couple more years, and that it was already time to begin working on an expansion of harder problems that would better test AI's ability to do math at a level that would actually be of interest to professional research mathematicians. So this was our 4th tier, 50 extremely hard problems, all developed by research mathematicians, each of whom had significant experience with the FrontierMath models due to being provided access to them and being able to do experimentation with these models. This culminated in the symposium we ran back in May. Around 30 mathematicians spent a whole weekend just proposing and writing problems and testing all the candidates they had against each other, trying to get a sense of what the models can and can't do, and ultimately putting together the best data set of problems that we could manage. Oh, and I just dropped the banner that I used when I made the announcement. So these guys were the judges of the symposium. So each sort of presided over a different field and made sure that, or helped provide feedback to the other researchers on getting the problems to be of a standard that would be suitable for the project. Shane Ken isn't here right now. And this is on the web page, but I figured I would pop into the slides of one of the tier 4 sample problems. So 2 of the 50 are part of the public sample. This was by our resident analyst, Pata Ivansvili. This was actually from a research project of his from about a decade ago that was generalizing some project to a discontinuous case. And he ended up deciding not to publish it because the ratio of effort of this problem to what he perceived as the interest at the time was too high to bother putting together all the details. But when he joined this project, this seemed like the right time to at least write down at least one of the cases of this project and turn that into a concrete problem. So in this case, this is a problem where the answer is not integer. C is encoded as a SymPy symbolic real number. And the way that it would be checked that a model has correctly solved the problem is, 1, we impose a reasonable character limit on how long the solutions can be, and then demand a level of accuracy of the input expression to the intended one up to a number of digits significantly beyond the character limit. The point being that we don't want to rely on standard equality checks for symbolic real problems. A single real might be represented in many ways, and the standard algorithms for simplifying differences to 0, if it is 0, are still imperfect. So it's better to do a high digit accuracy check.
Models allowed to use any tools or write programs?
Yes.
Do they do it?
Yes, they do try to use Python and Sage.
Did you compare their with and without that?
We've done a little bit of that, and I think for our evaluation of ChatGPT agent, we did post some statistics on that. It is a pretty precipitous drop if they don't have access to the tools.
So that's good.
Yeah, so it's a good sign that they are genuinely using these things. But for a problem like this, you really can't get anywhere just by trying to do an estimate. This little guy right here with the big negative exponent would never show up in any sort of experimentation. You'd have to actually see the concept underlying this problem to know where that comes from. So on our initial evaluations of the tier 4 problem set, the top performance was 3 out of 50. An impressive 3 out of 50 by O4 Mini. And at the time, none of those were super exciting. So yeah, I mentioned a little bit about our difficulty in guessing how hard a problem will be in advance. There's a common case for why a problem might end up being much easier than anticipated, which is unfortunately, there's a vulnerability in the problem that makes it somehow possible to guess with high likelihood the solution without really going through the key mathematical concepts, such as sometimes an unjustified but it turns out correct assumption can make a problem much faster to solve and still get what happens to be the right answer. So we do our best to prevent this in our review process, but it can be hard to predict in advance all the possible ways in which a problem might get shortcutted. And one of the ones that was solved was, so exactly one analysis problem was solved among those 3. And that was the one that our judges had determined to be the most mathematically deep and likely to resist AI for years. So turns out, again, that's just the common theme. It's hard to predict. So the author of this one, Yanjin Han, so for tier 4, we always show the solutions to the authors for commentary once that is solved. He says it did not follow the reasoning he proposed. Instead, he changed the problem from, I think he said it was a delay problem to a recovery problem using information theoretic insights. And turned out that was a much easier problem and for like some subtle coincidence that happens to get the exact same answer. Yep.
When you showed on the previous slide, what tier was that?
This one?
That was tier 4.
Yes. Since then, so we always evaluate any new new frontier model that comes out with the full FrontierMath suite.
So, just to clarify, acceptable answer to the previous tier 4 problem, could it be a numerical approximation to that constant, or it has to be that form?
It can be anything that can be understood by SymPy, Python symbolic reasoning package, but
It has to be symbolic. It can't be like a 10-digit approximation.
you can put in a 10-digit approximation. That would not get you the correct answer, though.
Well,
So
100-digit approximation.
So that's the thing. So to prevent that kind of, to prevent from just trying to brute force it with calculation, that's why we have a character limit. So the character limit is well below the level of accuracy required, so that it's virtually impossible to meet the accuracy check without actually having a correct symbolic expression.
What's our feeling about answers that are wrong proposed by the AI? Are they reasoning or they are just gibbering hash?
Sometimes the models just know. Sometimes we'll see that they'll try some things, go nowhere, and input 0 at the end. Sometimes they'll confidently say something false and follow that to the bitter end and get an absolute gibberish answer. Or at least, like, gibberish is not even fair. Like, it will reason soundly with respect to whatever false hypothesis it accidentally introduced at some point. Or maybe it even knows it's doing that, but thinks that it might be able to reward hack by introducing a hypothesis that makes the problem solvable for it. We see all those behaviors. So right now, the best score we have seen is only a bit higher. GPT-5 High was able to get, well, actually, I think medium and high both got the same score. But GPT-5 was able to get a 4 out of 50, which is not in of itself much beyond O4 mini. But what's a bit more interesting is that among all the problems that have been solved at least once throughout these runs taken together, 9 of them have been cracked at least once. And multiple of these successes, especially from O3, GPT-5, and Gemini 2.5 Pro, have demonstrated mathematical insights far beyond what we were expecting to see at this time and far beyond what the authors had been anticipating. And for these ones, it is confirmed that the model strategy did roughly line up with what the author intended to be the right way to tackle the problem.
Just to clarify, the models are not allowed to interact with a human while they're tackling the problem.
No human involvement. And also, for what it's worth, currently we have no web access allowed during FrontierMath runs, but we are interested in seeing how much of a difference it makes once internet access is provided. The problems are all designed not to just be simple, apply one paper and crack it style. So we think it will still be robust to full-on internet augmented evaluations, but for at least for consistency, we've started off with a no internet version of these evaluations.
Is there any like time or compute limit that you impose?
There's a time limit, but that tends not to be the bottleneck so much as tokens as a resource for models when tackling this. So the models do have a specific token allotment that they're given per problem. They're explicitly told this. They're explicitly reminded if they're not using all their tokens.
Like a
Compute limit, yes. Yep.
How do you decide how hard a problem is? Is it just based on what humans think is hard?
Roughly, yes. So most of the writers and the reviewers are heavily overlapped. We usually have the mathematicians try to review each other's problems within the same fields, and we collect. So I don't go into this process in these slides, but we have 3 sub-difficulty rankings where we ask the mathematicians, okay, for this problem, how long do you think it would take you to figure out or to find the key insight? And once you do find the key insight, how long would it take you to work out all the nitty-gritty details and get the exact answer? And also, how much background knowledge you need to even begin tackling this in the first place?
But you also rank it by like the length of the solution, in terms of like the length of the reasoning chain that's required in the abstraction level of the chain. It's like, have you tried to like evaluate for that?
Not rigorously, but qualitatively, it does seem to be pretty well correlated right now with what's hard for models. Just literal, raw, mindless measuring by solution length.
Did you try to evaluate the confidence the model has in the answer, either by asking it or by letting the model, offering to the model producer, you can also give us a confidence score?
We have not tried that. I think in a future iteration of this, one thing I would like to try is a scoring system where there is punishment for bullshitting us and doing the sort of SAT style. If you get this wrong, we'll take some credit off. But if you say nothing or acknowledge you can't do it, we give you just a neutral 0. And I'd be curious to see how well the models would do on this and if they would actually be willing to fess up about their weaknesses.
I was wondering if we know what the performance of, say, 100 grad students or postdocs, actual humans, if they, like if we took 100, say, divided between specialties, say 5 different specialties, they might achieve a similar percentage, given a fixed amount of, a maximum time.
Well, that also gets us into question about to what extent are the problems of public information and what extent are they held back?
Yeah, so let's go into these at once. We did try this experiment. So actually, we ran a frontier math competition back in Cambridge over at one of MIT's buildings back in, I think, March, where we had an open invite for math majors and grad students and professors to come on in, and broke them off into teams and gave them 4.5 hours to tackle each sample of the problems. It is. There's a lot of difficulties with doing this experiment in a way that is scientifically sound. Like, one issue is we couldn't include any problems that had a very long solution. If a solution is 10 pages long, then it doesn't matter if a person immediately sees the trick to it, the time limit will screw them over. So
Humans also allowed to use tools and
they were allowed to, yes. So we had to do like a non-representative sample to make sure that the problems were at least potentially reasonable, be solved in the time frame. And we did some amount of effort to have teams have diverse fields represented among the participants, but several of the teams were just friends who just really wanted to work together, and we allowed them to do so. So it's hard to really make sense of what is the canonical human score on frontier math, and obviously due to the extremely high diversity of problems, it's certainly the case that there's no individual human who knows off the top of their head all the relevant theorems being tested. Presumably, a specific telematician could eventually study another field long enough to tackle problems outside their field, but already, like, the knowledge base is already superhuman in what it demands. But we ran the experiment as I described it, and the best human team slightly outperformed the best available models at the time, which I believe was either 03 mini or 4 mini score.
Across models, did you see maybe similarities or differences in how they tackle one specific problem? And I guess, were there certain patterns on which tools that these models tended to use versus how like a human might go about it?
We do have some, we have begun like a process of doing model-specific long-form evaluations where we take a model and run it through FrontierMath and also all the other standard math benchmarks, and have some of the mathematicians who've contracted with us just look over this data and give their own experiments with it, and basically spend a couple weeks really just getting our best possible assessment of a model. So we did this with Grok 4, like it was a month or two ago. The full report can be found on our website. We hope to do this with some of the other labs, and that would probably give a lot better insight into really what it is that makes each model tick. But yeah, with Grok 4's evaluation, we definitely saw some oddities. We saw some geometry problems that Grok 4 did get the correct answer for. It just completely ignored how any human would do it, and instead did the most disturbing to look at coordinate bash to break through a problem that could not possibly have been performed by the relevant human competitors that this problem was designed for. So things like that we saw, but I would say on most of the time, when a problem is solved, it's usually within basically what the author intended, outside the aforementioned situation I mentioned about if there's a vulnerability.
Just to be clear, these, in your own internal evaluations, there was not access to the literature. Like, you couldn't look up paper on archive and look for the relevant theorems.
It cannot, but so part of the reason why I kind of want to shift away from this offline version is that at this point, the models have so thoroughly internalized the literature, it becomes kind of just which ones are lucky enough to show up in memory. So one funny incident we had recently was there was a problem that was solved by one of the models recently. I think it was 04 mini, and the problem, well, so this is not optimal design. This particular problem was relatively easily crackable once you know like the right theorem from the literature. So the model gets the right answer, and we look at its trace, and it cites a paper. It says, yep, I just used the formula from this paper, and that solved the problem. And the paper title was hallucinated because the model was offline. It doesn't have access to the internet. it vaguely remembered, or somehow that paper got into its training data, including the formula that solves the problem, but it didn't remember the title, and it made up a guess for what the paper's title was. So it was a pretty funny result to see.
Sympathize people.
Or just like cite every possible paper that seems relevant to whatever my paper is about today. Yeah, it's a very human behavior for what it's worth. But yeah, so I think it's kind of arbitrary, and at this point, I'm much more interested to see how they apply knowledge and what they are lucky enough to remember at any given time. So I think in the future, a more online-based evaluation system would be more informative. So here is Dan Romick speaking about O3 solving one of his tier 4 problems. So this is not a public problem. I can't actually show you the problem, unfortunately, but I did show Dan the reasoning trace, the raw unabridged trace that really shows the insane amount of length that is going under the hood as they're spending tons of tokens and an internal monologue working their way through a problem. And eventually it stumbled on like the right idea for tackling it, and this was his assessment of it. So this unpublished asymptotic analysis technique, even if they've read all of Dan's papers, which I'm pretty sure it has, it still has to do some amount of genuine generalization, the same as he did back in 2003 when he had first stumbled upon the idea that he never wrote up until making this problem. And another one of the problems that got solved recently was an algebraic geometry problem submitted by Ravi Vakil. Again, his assessment was overall, he thinks that the reasoning trace reflects pretty much getting the main ideas he had intended behind the problem he had submitted. But I still have some Achilles heels. So I asked earlier if anyone could guess which of the sample problems on the webpage remain unsolved. 3 of them are ones you probably expect. The 2 ones that are tier 4 unsolved, one of the tier 3 problems unsolved, and then there's just tier 1 question. It's a very elegant planar geometry question with a competition style flair to it, based around a rather cute phenomenon involving a calculation that would be intractable by brute force, but it turns out most of the things that almost in lines cancel out, so there actually is a rather simple program you could do to compute the answer. It's a very simple epiphany, but it's very visual, and none of the models have made this epiphany. And also, the author is an MIT undergrad. So, having seen the solution, we looked at this and was like, okay, that's a simple problem. Good tier 1 problem, very bright undergrad you got here, but did not expect that this would be one of the problems from the original problem set to resist being solved for the longest. So, okay, so I just showed you quotes from very good professors of math, lauding model solving its problem, and also it cannot solve some basic geometry problems. The frontier is really, really jagged in mathematics right now. So putting this all together, what can the models do and not do right now based on what we've seen in these evaluations? Well, the ones that score really high can definitely have very great facility navigating the literature. Obviously, they do better at this in online evaluations, but again, because then they have so much memorized knowledge, they might as well be online, whether or not it is. So they can search through the literature, look for the right concepts, sometimes several of them that need to be combined together, and they can faithfully apply theorems and engage in, I made this phrase right now, quasi-rigorous reasoning, where it's like as some sense of what it means to have a legitimate mathematical deduction, and it will sometimes call itself out if it catches itself not reasoning rigorously, or catching itself finding one observation that contradicts something else and realizing, oh no, something must have gone wrong. but it's still pretty far away from the level of precision that a human has, where we really know when we are making legitimate, fully or tight deductions. Well, on the con side, they lack visual intuition. Any problem where where a human would think about the problem visually or geometrically and resolve it that way without engaging in words-based reasoning and not having an obvious formula to throw at it. These kinds of problems are just a big problem for the models. So on tier 4, none of the problems from the geometry/topology section have been solved yet, and only a few of the geometry problems from our original FrontierMath dataset. But just like overall, like the most glaring absence to me is there's just no drive in these models to really explore an idea that isn't immediately relevant to whatever objective or whatever that is being tasked of it, and no semblance of research taste. So even in the really hard problems it is solved, it is still ultimately playing this game of, okay, of the concepts I know of, what's the one that's most relevant here? Try that, try the next second best one, try the third best one. And look, in fairness, that is also a large percentage of what we human mathematicians do when we tackle problems. We aren't having big, brilliant epiphanies every day, or at least I'm not. But it's going to need more than that to really achieve true superhuman capability. And just taking the architectures that we've seen now and scaling those up and improving those, I can see like the scores continuing to improve on these benchmarks, perhaps towards saturation. And it's still not towards reaching the objective that I think most of us would really want to be able to see, that a model able to just start engaging in the analysis of structures simply because they perceive that as being whatever is most informative or what it's most curious about, and organically and efficiently developing its own access to and source of mathematical knowledge. So I'm copy pasting here a slide from earlier where I listed some criteria that I think are important of a large-scale math benchmark. In terms of how well I think my own benchmark fits on this. So in terms of the high difficulty ceiling, I think it's certainly one of the strengths of this project, and certainly beats out most of the pre-existing math benchmarks. But it's still not, the ceiling is not at the point where if you master FrontierMath, I'm willing to say you are a superhuman mathematician or that humans need to retire. Like, that's not going to happen when this benchmark is saturated. The difficulty ceiling is not high enough to justify that, because ultimately it's still just solving known problems and toy cases provided by the professionals. Definitely succeeds on the automatic testing and verification part. That was just pretty fundamental to how it was designed. The gradual increase in score scale was improved, I'd say so. The only really big jump we saw was from the reasoning architecture as shown off by Gemini 2.5 Pro in 03. Those models got scores that were well beyond anything that we had seen before. But that jump since then has given way to a more smooth progression of performance. Definitely did not succeed on the well-calibrated difficulty order, as shown by the fact that there's still a multitude of tier 1 problems that need to be solved, and conversely, some tier 4 problems were far overestimated in their difficulty. And finally, in terms of multidimensionality, I think the benchmark does do a good job of that. It covers most of the major fields of math, but they weren't really well organized as such because we didn't even know what were the key capabilities that would be tested. Like, I hadn't isolated beforehand that we would want like a substantial visual reasoning component to see when that sort of hole would be filled. So that would be something that's more directly looked out for in future projects.
Excuse me.
Yep.
What's the reason for that sudden jump by 03? Is it just a sudden increase of number of parameters?
Not scale. There are larger scale models, even at OpenAI, than O3 that don't do nearly as well. It really was the shift to reasoning architecture that was really necessary for models to start doing well in math, because models have a high error rate on a step-by-step level, but they can lower that step-by-step error rate much lower if it then is able to like look at its own tokens and reflect and identify potential errors and cross those out and refine its analysis. So we're running out of time, and I would like some time for questions. From what you're talking more about this later, the end of this presentation was mostly just me giving some ideas for what I think would be natural follow-up projects that I am considering, such as one being an open problem curation benchmark, since I don't think after tier 4 we want to have just more contrived problems. At that point, is we really just want to test it on its being solving the things that are open and we care about learning the answers to. Definitely want to do some more investigation into formal math benchmarking. FrontierMath was, like I said, an informal math benchmark, and I think it's hard at the moment to do good formal math benchmarking due to the fact that MathLib is still rather sparse in the topics it covers. So I would actually, if I were to start doing formal math benchmarking, focus more on auto formalization testing rather than problem-solving capabilities in such models. So you also asked me a little bit later about how I would automatically check that a model has correctly formalized the statements of a math paper via checking, doing unit tests on its ability to prove correct corollaries. And finally, I'll just end up with one last thought experiment, which is the idea I've been having regarding Fermat's last theorem, which is, I think many of us would agree, is a pretty iconic example of how powerful the mathematical method is. That a very simple to state theorem, conjectured or stated as a theorem all the way back in the 1600s, but was only ever really solved thanks to centuries of really deep advances along many axes, most of which weren't even intended to be relevant for Fermat's theorem. So I have this thought experiment of, what if we went back in time and tried spurring faster progress on Fermat's last theorem by offering our forefathers all sorts of incentives to be the first person to solve it, and offering untold riches and glory if you are the one who proves this theorem? How much do you think that would speed up or slow down progress towards Fermat? Anyone want to speculate their opinions?
Topic for discussion. Why don't you
Yeah.
actually talk and we can discuss?
Okay. Yep. So one last slide is just so my final idea for a project to really test AI's abilities to come up with truly genius accomplishments would be to do what I would call a vintage AI benchmark, where you're not really testing a model so much as an architecture, where if you claim that some architecture is like a brilliant advance, you then retrain it on a limited data set so that it only has access to knowledge up to a certain point, and seeing to what extent this is able to, with the knowledge at the time, retread the steps of our ancestors, or even come up with a different path towards acquiring the great knowledge that we have today. So those are some ideas that I'm looking forward to trying to implement over the coming year. Thank you.
Just the immediate thought about your idea theory, is anybody taking snapshots of the, I mean, there's some sense of snapshot in the archive. That would be something to have to make this possible.
It's definitely good. There's definitely a lot of curation of data that would have to be done to put this idea into practice. So I think that it shouldn't be. I think there's all sorts of backups that are being done on current math literature. Probably it would be much harder to set up an experiment like simulate what Wiles knew when he was tackling Fermat's theorem, simulate what Grothendieck knew about algebraic geometry when he invented scheme theory, and whether the model can make the same generalization from the same data set as he did. Those would be very tough to set up, but I think it would be very informative to do so.
You just, because I'm not sure you said it, so the status of it is that somebody who has a model can request that the AI, please, benchmark the model. That's the base state
It's not that simple. So the problem is that there's no foolproof way from a security perspective, of running an evaluation. So if the problems got leaked to the public, within a few weeks, all of the solutions would become public because people can't help themselves and would solve all the problems and post the solutions online. And then it stops being a useful benchmark. So we only run the models. We only run it on models that, one, are reasonably likely to actually have a non-trivial score on it. So we need to see some evidence that you're from a serious lab or that you have made serious mathematical research, and really make sure that your security agreements and legal agreements are airtight so that they don't just mindlessly fish through their logs to try to reconstruct all the problems and then disseminate them.
Yes, but you bet we do that.
Yep.
I think there were at least a couple of mentions of tier 4 problems being made from some subcase or something that a mathematician thought about but didn't end up publishing, right? So something that was unpublished. So at least on Archive, you have access to the text source of the papers. And I wonder if occasionally people might leave partial progress commented out so that it's not on the so that it's not on the PDF. But maybe they wrote oh, if you compute this, and that, maybe I could get this, but it seems like too much trouble, I won't do it, and then just comment that out. I wonder if that could affect the solvability of some of these tier 4 problems if the model sees that.
I mean, if that was what happened with any of the mathematics behind these problems, when they tell me that their problems are unpublished, I think they're including archive posting as publishing it. They literally never got around to ironing out dotting all their I's and crossing their T's and posting a proof. But they've known for a long time it's true, and they didn't really have much use of it. So this was the most useful thing they could do with their result. Yep.
Have you tried to see if the models can themselves generate FrontierMath type of problems?
Not really. I occasionally ask them, one of my favorite experiments every time I get a new model is show me an interesting idea involving the axiom of choice, my own area of research. So far, I haven't been impressed by what any of them have come up with. FrontierMath has a pretty specific format, so.
You have to turn it around.
It would be very impressive. I would be quite impressed if they could make this benchmark themselves.
Just to generalize the question a bit, because there are lots of projects like that. You could have language models today, all sorts of things. And so suppose a researcher came to said, here's my proposal for how we're going to test a new thing, and again, these examples. Would you consider some protocol to make that possible? Whatever. I mean, I guess you're not the one to speak for that.
So that sounds possible. So one thing that I sort of take a bit of inspiration from is the fact that the AlphaGo and AlphaZero style models were able to master 2-player, well-defined board games through lots of self-play. So it would be very helpful if we could get math into this format. I think this would be a good idea to try, especially on a formalized benchmark where what is lean but just a really, 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 really complicated board game. But okay, we would need some sort of competitive 2-player element to finish the analogy. So you can imagine some sort of well-defined arena where it's like the 1500s Italian mathematics duels where models say, I know how to prove something I bet you can't do, and designing challenges one another in a competition. So maybe that could work well enough to be self-trained on. Yes.
What was the process like determining how much compute the models are allowed to have to tackle each problem? And does it change but when you evaluate on like tier 1 through tier 4?
It's a bit higher for tier 4, but the process was mostly what seemed reasonable for us from a budget perspective. It's certainly high enough that we don't think that any of the models are being held back by lack of higher compute. And it's actually a minority of the time that the models will bother using all their tokens. Son?
So, it seems like the most common tool these models like using is like Python programming. I mean, do any of these models like have access to like Mathematica, and has that been like, have you evaluated models which call tools like Mathematica?
I don't think we've seen that behavior. I mean, for rather arbitrary reasons, the things the models are most used to is Python. Obviously, the companies want their models to be very good at using Python, so that capability is there, and that is often good enough for the computational needs of a problem, unless Sage is usually the next best thing for them if there's an actual high computation algorithm that has to be implemented. The one funny thing we saw was, okay, so we did do one online full evaluation. This is not in our table because it's not an apples to apples comparison, but we did experiment with ChatGPT agents with web search on, since that was one of the things that what the model was particularly trained for. And this resulted in a couple of problems that had never been solved before being solved. One being one that had involved like a heavy use of a computer algebra system. So we had to go find one that it could freely access and just run the calculations there, and it worked. And I think the other one, I think it was like a knot theory problem that needed some really niche algorithm. So it found like a repository that had this algorithm fully implemented and downloaded that and implemented and solved the problem. So they're pretty resourceful at using the tools available if they are allowed to run rampant.
Based on these kind of benchmarks, like, are there any kind of general direction in terms of like where AI research should be going that you guys are getting sort of inspired? Because, for example, like when I think about the DeepSeek math paper, the really interesting part of that was that training the model on a lot of kind of coding related data set ended up, having a big result on like solving math. So based on maybe how different models are performing on these benchmark tests, maybe it's the way they're solving it. Does it give you like a potential direction in which we should take future like model training in terms of like which direction we should be taking?
I think a couple of things that I think should be relatively easy to implement that I can see making differences. One, better willingness of the models to acknowledge they are on a futile path and start over. So one phenomenon I didn't actually mention so far is that we do multiple evaluations per model at once, or like in parallel. I think it's 8 or 16, and we keep track of their pass at 1, their pass at 16 scores. It's still again like, and if the models were sufficiently efficient with how they spent their tokens, especially knowing that they don't usually spend all their tokens, then it feels like they should be able to consider all their approaches and just choose the best one and have a pass at 1 similar to a pass at 16. But that's not at all the case. I think the pass at 16s tend to be like 50% higher than their pass at 1 scores. So best I can tell so far is that it seems like the models, if they start off on a bad foot, they stay on that bad foot, and they can locally notice that I'm making some bad deductions right now, but not as good at saying, I am strategically not thinking about this problem right. Let's really look at this from a fresh perspective. So that's one. And yeah, the other thing that's on my mind is what I've said before, that I think that to really get models that are deeply capable or really matching the heights of the top humans, they have to have some sort of internal metric of to optimize for when doing math work that isn't just solve the task right in front of me. You don't solve for Ma's last theorem by spending all day thinking you have increasingly complicated polynomials or something. You have to have some be trained towards making analyzing indirections simply because they are productive, even if they aren't productive towards what you thought of or like what you're told is the one problem that actually counts or something. So it's a very vague goal, but I think that is something that needs to be implemented in the models to have an actual semblance of human research in them.